Hi students. In this lecture, I am going to discuss problems based on motional EMF and Faraday's law. Let us see first one. Let's see the question given. A right angle triangle ABC made from a metallic wire moves at a uniform speed v in its plane as shown in the figure. A uniform magnetic field exists in the perpendicular direction. Find the EMF induced in the loop ABC, in the segment BC, in the segment AC, and in the segment AB. Okay, let us see how to start. So first of all, make the given diagram. Let's see given right angle triangle. So it is make the diagram. And we can see field is now normal to plane of the board. It is outwards. So this is given A and B, and this is C. Field is now normal to plane of this board and outwards. And let us consider both the plane as xy plane. And this is given a velocity v, which is right side. Now see what is one. Moves at a uniform speed. So speed is a constant. So first we have to find out EMF induced in the loop ABC. If you focus carefully, because of motion of this loop, there is no change in the flux through this loop because the field is now in this entire region. It is now in the entire region field is. That's why even though loop is in motion, there is no change in the flux through that loop. That's why EMF in the loop is zero. So it is now EMF in the loop ABC is zero. Okay. And now see what is asking here. Next one in the segment BC. Now, if you focus BC, now see what happens. So we can take now motional EMF, that is E equal to L bar dot V bar cross B bar, right? And you can see here velocity vector along x-axis, field vector along z-axis, and L bar along BC. You can say along y-axis. So all three are mutually perpendicular. Okay. So I can write directly E value across BC. That is equal to, it is BLV. Okay. I am taking BC length as L. This as L. So BLV, right? And we can see if you want to find or if you want to decide is which point is at a high potential. Is it point B or point C? Then see what we can do. If you are focusing only BC, I am focusing here force acting on electrons in the wire BC. C1 F bar equal to Q into V bar cross B bar. We are now just focusing on direction of force on electrons in the wire BC. Okay. So since electrons means charge negative, so I'm taking negative here. V bar, velocity along positive x-axis. So it is I cap cross B bar. B bar is now towards us. That is a K cap. So I cap across K cap. That is minus J cap. And minus of minus, it is a plus. This is now J cap. That means electrons moving up. That means B becomes low potential and C becomes high potential. Cross check once, charge negative, velocity, it is direction I cap, field, direction K cap, I cap across K cap, it is minus J cap, minus of minus plus J cap. That means if you want to replace with a battery, it should be like this. Wait, B should be low potential because electrons moving up, that is low potential. It should be like this. Okay. Like this, we can represent BC. Okay. Next, C focus. In that, what else we have to calculate? Next, in the segment AC. In the segment AC, you can see L bar and V bar in the same direction. And we have learned that out of these three vectors, if any two vectors are parallel, no EMF is induced. That's why across AC, it is 0. Okay. Next, focus in which segment it is across AB. Now coming to AB, velocity is now like this. Let me take this angle as theta, then this also theta. Now what I'm doing here, I'm taking for velocity two components. One is a parallel to wire, other one normal to wire. Okay. I'm taking for velocity two components along the wire and normal to wire. This is a theta, this also theta. This is V cos theta, and this is now V sin theta. And just now I have discussed that if any two vectors are parallel, no EMF is induced. Therefore, because of this a parallel component of velocity, no EMF is induced across AB. EMF is only because of this normal component. Therefore, E value across AB, that is equal to, let us consider the AB length as L2. AB length, okay? Or take this as L1, that is L2. Then this is L1, right? For EAB, that is equal to B L2 in the place of V sin theta. Okay. And you can see from this triangle, if this is a theta, sin theta will be opposite by hypotenuse. That is L1 by L2, right? If you take in the place of a sin theta, L1 by L2, L2 gets cancelled. It will be BL1V. That means EAB is equal to EBC, right? Next, focus which end is at high potential. Is it A or B? Okay. Now, we can do one thing here. Across AB, there is no EMF is induced, right? That means here A and C are at same potential. Get the point. A and C both are at same potential. That means coming to B. See now what I can write. Or we can do one thing here. Let us see force acting on electrons in the wire AB. Okay. Then force acting on electrons. Now I am taking here for our convenience. normal to the wire as x-axis. This is completely our choice. So for our convenience, I'm taking as normal to this wire as x-axis and parallel to wire as y-axis. Okay. Now take again same logic. Charge negative for electron. Direction of velocity. It is along positive x-axis, that is I cap. Direction of field, it is outwards, that is k cap. It is again j cap. Again j cap means electrons move towards B. So this is low potential and this is now high potential. Okay. Or directly we can say from here, AC, both are at same potential. Okay. Because there is no flow of current. That's why same potential. No EMF is induced. Same potential means when you compare BC, C is now at high potential. In such a case, AB. When compared to C, B is at low potential, right? See here, when compared to C, B is now at low potential. But A and C having same potential. That means when compared to A, B will be at low potential. That means we can replace now AB with a battery like this. Okay. So if you draw a complete circuit, see how that will be. It is now like this. So both have same values, same EMF. Then you can see in this complete circuit, what is now net EMF? That is equal to 0, right? That's why EMF induced in the entire loop ABC equal to 0. So like this, we can decide which point is at high potential, which is at low potential. Here, B is now at low potential compared to C, right? In the same way coming to here, A and B. So A is at high potential compared to B, right? Since no net EMF, there is no current in the circuit. I equal to 0. Okay. Let us see next one. Let's see the question given. Consider the situation shown in figure. The wires P1 Q1 and P2 Q2 are made to slide on the rails with the same speed 5 centimeter per second. Find the electric current in the 19 ohm resistor if both the wires move towards the right and if P1 Q1 moves towards left, P2 Q2 moves towards the right. Okay, let us see how to start. So first make the given diagram. So two metallic rails and having two conducting wires which can slide, given P1 Q1. So it is given P1 left one, P1 Q1 and right one. It is P2 Q2. Field is now into the board. Let us take the board plane as XY plane and each having resistance 2 ohm, 2 ohm and 2 ohm and having here one resistor. Its resistance is 19 ohm, right? And you are given this length equal to 4 centimeter. Now see the first condition. Find electric current in 19 ohm resistor if both wires move towards right. If both are moving towards right with a velocity, and see velocity given 5 centimeter per second, right? Right side. So when they are moving right side, see how we can replace these moving bars. So first I'm deciding which end is at a high potential, like is it P1 or Q1, okay? First I'm taking here F bar equal to, again Q into V bar cross B bar. V bar cross B bar, charge negative, focusing electrons. Velocity given right side, direction is I cap. So I cap cross field minus K cap. So I cap cross minus K cap, that is J cap. And having here minus, it is now minus J cap. Okay. That means electrons will move down. So we can replace now P1 Q1 with a battery. It is like this, having resistance 2 ohm. In the same way, P2 Q2 again by battery of same EMF, because both having same speed, right? Now circuit is like this. It is 19 ohm. Okay. And see what is that EMF induced. That is equal to L bar dot V bar cross B bar. And you can see here L bar, L bar, V bar and B bar. All three are mutually perpendicular. So its value is B, L, V, right? And see how much value we are going to get. Substitute values in that. B is given 1 and L value 4, 10 power minus 2, converting into meter, and velocity 5 centimeter per second. So this is how much? 4 5 20. So 2 10 power minus 3 volt, right? Okay, now see what we can say. So by symmetry, for example, if I current is flowing in 19 ohm resistor, which we have to calculate. Then coming to here, I by 2 in this one, remaining I by 2 in this, right? Divides equally. So now here what I am saying is, you can see potential difference across this and across this. Both are same because these two are parallel. So I can write 19I should be equal to EMF is 2 10 power minus 3 EMF minus I into R. It is I by 2. I by 2 into R. R value 2, right? Because it is now discharging. Okay. So 19I is equal to, means very equate now potential difference across P2 Q2, or you can say across P1 Q1, that is equal to across 19 ohm resistor. Now see calculation, 2 gets cancelled. Take this one to here. 20I is equal to 2 10 power minus 3. And 1 2 gets cancelled. So I equal to 0.1 milliampere, right? Like this we can calculate. Now see the next one in that. If P1 Q1 moves towards left, P2 Q2 moves towards right. That means see how circuit will be. The only change is now coming to P1 Q1, which is moving left side. Now upper one becomes low potential and lower becomes high potential. This is now circuit. Remaining part no change. Right. It is now like this. Then see what happens now. Coming to EMF, no change in that. Same. Let us take in this one current is I. Now coming to here, what we can say. Is there any flow of current in the circuit or not? Okay. Right. So coming to here, this is low potential, this is high potential. That means if I am focusing P1, P2, Q2 and Q1. See now in this part, or if you want to replace these two with a single battery, then how to replace now this? See, if you want to replace these two batteries with a single battery, so first I'm replacing these two batteries with a single battery. Okay. For that battery, what is equivalent EMF? Okay. Then see what I'm doing here. For the time being, assume this is not present. Okay. Because our intention is to replace these two cells with a single cell. Then, if this is not present, current flows only in the circuit. Okay. I am taking current TSI like this. I can say some I dash to avoid confusion here. Then this I dash current flows like this. Or I will make diagram separately. Low potential, high potential, resistance, high potential. This is low potential, again resistance. Let us take this current as some I dash. This is I dash. Now I am taking here Kirchhoff's second law. See carefully. Suppose starting from here. We are moving now low potential to high potential. So plus epsilon, low to high. Next, we are moving along the current flow. So minus I dash into R. Next, again along the current flow. Minus I dash into R. Next, low potential to high potential. Okay, it is how much? Low potential to high potential. So low to high means it is now plus epsilon that is equal to 0. Right? Cross check once. Low to high potential. Next, along the current flow. So I dash into R minus. Again, along the current flow. Minus I dash into R. Low potential to high potential plus epsilon equal to 0. Now see what figured I dash equal to 2 epsilon by 2R. That is equal to epsilon by R. Right? Minus I dash R minus I dash R. 2 I dash R. 2 epsilon. Right? Now see carefully. Potential difference across P1 and Q1. Across P1, Q1. Okay. Then see how much we get. Potential difference. You can see from this current direction, both are now discharging, right? When it is discharging, potential difference equal to epsilon minus IR. It is now I dash R. Okay. So epsilon minus I dash. I dash how much? We got epsilon by R into R. This is equal to G. That means across this combination effective EMF, how much? It is 0. That means across this there is no potential difference. That indicates a current equal to 0. Okay. So I hope you got the clarity. So we are just focusing on writing the Kirchhoff second law, right? Let us see next problem. The current generator shown in the figure sends a constant current I through the circuit. The wire CD is fixed and AB is made to slide on the smooth, thick rails with a constant velocity V towards right. Each of these wires has resistance R. Find the current through the wire CD. Okay, let us see how to start. So first of all, make the given diagram. Given current generator. It is now current generator which maintains a constant current, right? So that maintains constant current. Field is into the board. And you can see one wire is, it is given CD. This is a CD. I think this is not moving, right? C1s, which is moving. Yes, wire CD fixed, okay? AB is moving. So coming to AB, it is moving. AB, it is moving with a velocity V, right? And the current is now given I. That's the question once. It is made to move on thick rails with a constant velocity V towards right. Velocity given constant. So we have to find current through the wire CD. Suppose current through CD, take it as I dash, which we have to calculate. So I dash value we have to calculate. Now see what we can do. First of all, I am taking this board plane as XY plane and I'm focusing which end is at a high potential, like is it point A or point B. So for that I am taking once again F bar is equal to Q into V bar cross B bar, right? Focus now direction part, force acting on electrons in the wire AB, okay? Electrons, negative charge, velocity direction I cap, coming to B bar, direction is into the board, minus K cap. So I cap cross minus K cap, that is J cap, and we are having here minus, so it is now minus J cap. So electrons moving down, right? That means if we redraw the circuit, or I can say, we can replace the wire AB with a battery. With a battery, electrons are moving down, therefore battery must be like this, okay, and having resistance, each of resistance R, right? This is now circuit. Now see what I am doing here. This I current comes like this. In this I dash flowing in this way, remaining flows in this way. Remaining how much? I minus I dash, right? So now I am taking for A, B, A, B, D, C, A. For this loop, Kirchhoff's second loop. See carefully. From here to, we are moving from high potential to low potential. So high to low means minus. EMF is BLV. Okay. Next, we are moving opposite to current flow. So I'm taking plus I minus I dash into R because we are moving opposite to current flow. Next, coming to here, we are moving along the current flow. So plus, sorry, not plus, we are moving along the current flow. So we should take minus. It is minus I dash into R, that is equal to 0. So just we have taken Kirchhoff's second law. Now we have to calculate I dash. Minus I dash R minus I dash R. It is a 2 I dash R, that is equal to, see what else left. If you are taking this two, remaining is now IR minus BLV. Okay. So now what we can say, I dash is equal to, it is IR minus BLV upon 2R, right? So it is just replacing that moving wire with a battery, equivalent battery. Then we have taken Kirchhoff's second law for this loop, right? So I hope you got clarity.